Hi friends, today we are going to see a new topic called as dynamic range scaling. Now, why this topic is so important? What do you mean by dynamic range scaling? Dynamic range scaling is done in a fixed point arithmetic for a digital filter. Why fixed point? In fixed point arithmetic, in some internal nodes in digital filter, it might happen that the number addition multiplication might result in an overflow. Because we are considering binary fraction, overflow means the leftmost bit, or we can say the left bit next to the binary point might convert to 1. Okay, that is overflow for us because that can be treated as a negative number also in sign magnitude form. So this type of overflow must be avoided. What happens if such type of overflow occurs? If such type of overflow occurs in a digital filter, then there is a large amplitude oscillation occurring in this IIR type of filters, especially, not in FIR. This type of oscillations are also called as limit cycles. So to avoid such type of overflows in a digital filter, we do some type of scaling on the internal nodes. So what type of scaling do we apply? That we have to study in dynamic range scaling. So let us consider a system to which I am giving the input as x of n and the output is let's say y cap of n. The system is having many nodes and I'm using some rth node. Now I'm at some rth node and there are k such nodes, let's say, and we are standing at the rth node. Now at the rth node, okay, the component ur of n must be scaled down such that it will satisfy the bound or it will not produce overflow. So we need to actually find a condition, okay, on which or we need to design a condition such that after applying that condition we can always say that ur of n will never ever produce overflow in the system. Okay, so we need to produce that bound or that condition. Let us say that, okay, we are assuming x of n, or we are assuming that all the nodal points and at input and everything I'm getting a fixed point number. So we are assuming that the number system that we are using is fixed point or fixed point arithmetic. Second assumption is that they are all fractional numbers. Okay, so they are all fractional numbers, so they will always be having 0 point some binary format. Okay, let us consider when they are 0 point some binary format, that means they are positive numbers, and we will also consider that there could be negative factors, but that negative factors will be designed or represented as 2's complement. We will assume that my input signal, that is magnitude of x of n, is bounded to 1. So this is the third assumption. So first assumption is we are using fixed point numbers, second is fractional numbers, and third is the input is bounded to 1, that it will not go above 1. It will be either equal to 1 or less than 1. Okay, so there are two bounds that we will be designing. The first bound that we will be designing is called as an absolute bound. So for an absolute bound, okay, let us consider the convolution at the node ur of n, okay, is equal to summation k goes from minus infinity to plus infinity. Let's say up to ur of n, the transfer function is fr of k, okay, x of n minus k. Okay, this is my normal convolution sum at the node u r of n. Then if we take mod of u r of n, that is the magnitude of u r of n, which is nothing but the magnitude of summation k goes from minus infinity to plus infinity f r k x of n minus k, okay, and suppose that then I will split that magnitude. Now we know that the magnitude of the input is bounded to be 1 or less than 1. So if it is 1, then the factor u r of n will be equal to this number. If it is less than 1, then the product will be less than 1 or less than this frkn. Okay, that's why my mod of u r of n can be written as less than or equal to modulus of summation k goes from minus infinity to plus infinity frk. Isn't it? Because we can say since mod of x of n is less than equal to 1, that means the input is bounded. Now, when will be u r of n be less than equal to 1? That is, how my u r of n will be less than equal to 1, that I have to find. That can only happen if this guy will be less than equal to 1. That time I can ensure that my u r of n will be less than equal to 1. Therefore, I can write that, okay, summation, the bound is like this, summation k goes from minus infinity to plus infinity, okay, mod of f r of k mod will be less than equal to unity for all values of r. If this happens, then what will happen? Then my u r of n will be bounded and it will not produce any overflow. So this condition is sufficient and necessary condition which we can follow for avoiding the overflow at the internal nodes. So if I am keeping, let's say, if I am scaling, if there is an overflow, then I need to scale it down. Then by what factor will I scale it down? So the input, okay, is scaled down by a factor of, what will be the factor? It will be scaled down, let's say, by a factor of k, which is equal to 1 upon maximum of r summation goes from k is equal to minus infinity to plus infinity modulus of f r k. Okay, so this is the bound, or this is the factor k which we need to use to reduce an overloaded the internal nodes. Okay, so this factor we need to imply if my internal node is producing an overflow. So if I am producing an overflow at the input, any node producing, then input must be scaled down by a factor of k, and the value of k is given by this bound. Now we have seen that the dynamic scale bound has been produced using time domain analysis. That is, we have used a convolution. But that same thing can be produced using a frequency domain analysis. In frequency domain analysis, I'll be using Fourier domain. So that bound that I will get is called as the L infinity bound. Okay, so L infinity bound is a frequency domain bound which we will be using in and we will be using a Fourier domain. Okay, so let us take the Fourier transform of the convolution, and we will get u r of e raised to j omega, which is equal to f r of e raised to j omega into x of e raised to j omega. Correct? That is a Fourier domain. So what will be u r of n? U r of n will be inverse Fourier transform, which is given as 1 upon 2 pi integral from minus pi to pi f r of e raised to j omega, okay, into x of e raised to j omega e raised to j omega n d omega. Okay, now if we take the bound, that is UR of n bounded, which is equal to 1 upon 2 pi integral minus pi to pi. Okay, now there will be two bounds. One bound is bound on Fr of e raised to j omega into bound on x of e raised to j omega. E raised to j omega mod is what? 1. So that I will not write. I will write this as d omega. Now if I consider that double mod x of e raised to j omega is less than equal to 1, okay, which means that the mean value of input spectrum is less than equal to 1. Then UR of n will never cross 1 if this factor will be 1. Okay, and that factor is denoted as double mod of Fr of e raised to j omega to the base 1. Okay, we can write here also double mod to the base 1. Sorry, to the base infinity. For this it should be base of infinity. Okay, it should not be 1, it should be infinity. So double mod Fr of e raised to j omega to the base infinity is less than equal to